Hello everyone, welcome to all in this lecture. So in the previous lecture I have discussed rectangular combined footing. In this lecture I am going to discuss trapezoidal combined footing. Combined footing is basically which support the two columns or two column loads. So we design for trapezoidal shape of combined footing in the two condition. The first condition that I am going to discuss here, suppose one exterior column is touching this property line. So this is the property line. Okay, and then here there is a exterior column, and suppose here is a interior column. Load on exterior column is Q1, load on exterior column, that is Q2. So we cannot give the projection on the left side beyond this property line. And in this case, suppose Q1 is greater than Q2, so we can go for the trapezoidal combined footing. Trapezoidal combined footing. In other cases also, suppose there are two columns. Q1 load is coming on the first column, and there is a Q2 load is coming on the second column, and one column is heavier than other column. So in that condition also we can go for the design trapezoidal combined footing. One thing you have to be remember on always apply, we will apply in the design of footing, then whatever the total resultant of this load will come at a particular line or particular point. So center of gravity should be lie on that line. Suppose this is the two column Q1 and Q2, and this is the trapezoidal footing. Suppose here the center of gravity of footing, here is the total load, that is Q1 plus Q2. So line of this center of gravity of this footing should be lie on this line. By doing this, you will get the uniform pressure distribution, at the base of the footing. At the base of the footing, right? So you can see in this figure, one trapezoidal combined footing is shown in the figure. So you can see this is the column load. Q1 is coming on the first column, that is exterior column. Q2 load is coming on the second column, that is interior column. X2, that's an distance between two loads, that is called X2. Here the X bar is the distance between center of first column to the resultant of the loads, right? So you can see X bar, and X dash is the distance between outer face of the first column to the resultant load. Okay, so that is X bar. So by this figure, you can say X bar will be equal to, X dash will be equal to X bar plus B1 by 2, because this is the B1. What is B1? B1 is the width of the column. So this is the circular square column, we can say B1 into B1. This is B2 into B2. Here you can say Q0, that is the actual pressure that we can get divided Q divided by area provided. I get your point? Okay. Now you can see this is the trapezoidal footing on two parallel side, B1 and B2. In this case, you can see there is a B1 is larger than B2. Okay. Cross section is mentioned in the cross section of column is mentioned in the figure. Length of this trapezoidal combined footing is L. And CG, this is the CG of footing, center of gravity of this combined footing. So to get the uniform pressure distribution, this CG should be lie on this line. On this line to get the uniform pressure distribution. Right. Okay. So we will follow all this nomenclature, whatever I have notation, I will follow B1, B2, L, CG, B1 into B1 cross section, B2 into B2 cross section. So always to solve the design problem and to design combined footing or any footing, always there is a procedure that you have to follow. So when you will follow the steps, follow the procedure, you will get each and every data and by step. So we will not get confused. So that's why I'm saying always use follow some steps and procedure. So first we will calculate total loads. Total loads, that is summation of two loads. Here combined footing is supporting the two loads Q1 and Q2. So we'll take the total load. Then we will find what are the area required. So that will be Q divided by QNA, where QNA is soil allowable pressure. Then we can calculate X bar. So X bar, how we can calculate? So we'll take the moment about this point here. So what you will see that Q into X bar will be equal to Q1 into distance. So this point and line is distance is 0 plus this resultant of load is okay. Now Q2 into distance from here to here, that is given X2. So we can calculate X bar, that will be equal to Q2 into X2 divided by Q. Q is the total load, right? Now we can go for the calculation of this X dash. So X that will be equal to X bar plus B1 by 2. Now we will see if X dash is less than L by 3, then we will go for the strap footing, it's suitable. What is the meaning of this? And in between L by 3 to L by 2, we will go for the trapezoidal combined footing. If greater than L is equal to L by 2, we will go for the rectangular footing. So I will explain what is happening here. See, when X dash is less than L by 3, it means L is greater than 3 X dash. It means distance between two columns are far, very really apart, right? So this distance between two columns is greater than compared to this footing, you can say. So what we'll do, if you will design the combined footing, so that will be economical. So to avoid the uneconomical, that will be to avoid the uneconomical or to make it economical, so we will go to design for the strap footing. What is the meaning of this? See, this is condition L is greater than 3 times of X dash. It means one column is here and one column is here, right? So we'll design the combined footing, that will be uneconomical. So what we do, we design is this is like a strip footing. And we design again a beam, and this beam we have as a connecting link between both footing. So this is called a strap footing. So this is called a strap footing. Sorry. Okay. So now when L by X dash is between L by 3 to L by 2, so we will go for the trapezoidal combined footing. When X dash is equal to L by 2, this is the condition if we have. So you will see when L is greater than equal to X2 times X dash. It means when you are provided the half of that is, this is X dash, you will multiply by 2 times, then it will give the L. So we'll see when you are providing the rectangular combined footing. So center point of rectangular combined footing at a half distance. So this distance is L by 2. Center of gravity will be lie here. And resultant load is coming also here because this is the x dash. So you will see center of gravity lying on the resultant of loads, right? So so we will get the uniform pressure distribution, uniform pressure distribution, right? So better we can go for rectangular footing when x dash is equal to L by 2, right? Okay. Now, then we will calculate width B1 and B2, width of two parallel sides of trapezoidal combined footing. So there are some relation. By using that we can calculate width B1 and B2, and those relation are, first we will calculate area. So what will the area of trapezoidal footing? So that half into length into L into summation of parallel sides. Summation of parallel side, that is B1 plus B2. So we can use this relation. Then one more relation that is very, very important to understand this relation. And what is this? See how we can we have calculated x tax. So we have calculated x tax from distance, x tax is the distance between outer face of this column 1 to the resultant loads, right? So we have calculated from the loads. Okay. Now CG, what will be the CG? CG from the larger side, there is a formula that you can remember, L by 3 B1 plus 2 B2, B1 plus B2. So this is the center of gravity. Always remember, see, when you multiply by 2 into B2, it means distance CG will be from the B1. If you will do 2B1 plus B2, distance CG from the B2. So now see, I have multiplied 2 times into B2. So distance will be from the B1. So that is, you can remember. So to get the uniform pressure distribution, this CG should be like on this line to get the uniform pressure distribution. So now we can say this distance will be also x dash. So we can write from here x dash is equal to L by 3 B1 plus 2 times B2 B1 plus B2. Means by using this relation, if you are using this relation, it means the uniform pressure distribution condition already we have considered, right? Okay, so by using these two relation, we can find B2. We have the L x dash, so we can find B2. So once we have the B2, we can calculate the B1, right? So now we have the B1 and B2. So here we will get B1 and B2, that is width required. What are the width required, right? So we can provide some extra width also to be safer side, right? So once we have provided some extra width, then we can calculate actual area or provided area. So once we have the provided area, we can calculate actual pressure, right? So we can calculate here. You can see in this relation, Q naught is equal to Q by divided by half into L B1 plus B2. So here B1 and B2 are the provided width. Here the B1 and B2 are provided width. So once we have the actual pressure, then we can find intensity at various points, that is UDL load, or we can say in this case uniformly varying load. And once we have that information, then we can also draw the shear force diagram and bending moment diagram. So once we have drawn the bending moment diagram and shear force diagram, then at any position, at any location, at any critical section, we can at any section we can find shear force and bending moment, whether it maximum or minimum, whatever. So once our task is to draw the shear force diagram, bending moment diagram. So in this combined footing, we will follow up to this procedure. If you are going to design the reinforcement concrete, so you have to find the whether it will be the critical section and what will the bending moment. So once shear force and bending moment diagram, then we can go for the what will the effective depth on all this reinforcement, all this. So from a geotechnical point of view, we have to draw up to the shear force diagram on bending moment. Let's discuss some numerical problem. so that we can understand each and everything. So see, design the trapezoidal footing for the two column shown in the figure below. Take allowable soil pressure as 200 kilonewton per meter square. That is QN is given. You can see the cross section of column are given 0.5 into 0.5. For the second column also 0.5 into 0.5. Loads given, that is 200, 2000 kilonewton, that is Q1, and 1500 kilonewton, that is Q2. Center to center distance is given. This is given Q1. This is given Q2. This is given B2 into B2. This is given B1 into B1. This is center to center between the loads, that is 6 meters. So here given x2 is 6 meter. Total length is given 6.5 meter. So we have all this information, and here this is the QNA, right? So we have all this information. So there is some procedure that we have to follow to design the trapezoidal combined footing that we will discuss here. So first we will calculate the total loads that we get 3500 kilonewton. Then we can calculate what are the area required, that we get 17.5 meters square. Then we can calculate x bar, that is 2.57 meter. Now we can calculate x dash, that is x bar plus b1 by 2, that we get 2.82. So once we have the x dash, now we will see x dash is lying in which range of L, right? So we will see L by 3 x dash is lying in the range between the L by 3 to L by 2, right? Means we can go for the design the trapezoidal combined footing. If this x dash will be less than L by 3, then we will go for the strap footing. If x dash is equal to L by 2, then we can go for the this rectangular combined footing. You can ask also, if sir x dash will be is greater than L by 2, we can also go for the rectangular combined footing, right? Okay. See, so now we can calculate their dimension width in parallel sides, that is B1 and B2. We have the relation. So see, we can calculate the B2 by using this relation, but in this relation, A is the required area, L and X dash. So when you will put the required area, then we can get the required width of B2. So B2 we get 1.62 meter. So B2, this is the required width. Once we will put the value of required width of B2, then we can calculate required width B1. So that we get 3.76 meter. So let us provide some extra width to be safe side, and we have provided B1 3.8 meter and B2 1.65 meter. So once we have the B1 and B2, we can calculate the provided area, and then we can calculate the actual pressure. So actual pressure we can calculate. Here B1 and B2 is the provided width. So we can get 197.6 kilonewton per meter square. 197.6 kilonewton per meter square. Now we can draw the shear force diagram and bending moment diagram. So to draw the shear force diagram and bending moment diagram, first what we have to do, we will draw a line diagram. We will draw a line diagram. In this line diagram, we will show what will be the pressure distribution. So once we'll have the pressure distribution and load and their dimension, okay, and their location distance, what they are locating at what distance. So once we have this information, then we can go for the draw the shear force diagram. Okay. See, this is the I've shown the line diagram. This is the you can see this is Q1, this is Q2, this is X2. Okay, and pressure. See, pressure, actual pressure we got what 197.6 kilonewton per meter square. This is the pressure. So now we can calculate the intensity on the right side. So you can see this is the trapezoidal combined footing. So their width is varying at always. Means whatever the length perpendicular to this plane is varying. Okay, so you can get that uniformly. This UDL is varying throughout the location. So we can calculate later. So intensity at the site B2, we can calculate actual pressure into perpendicular distance, uh, perpendicular distance from this plane. So that is B2. So we can calculate 197.6 into what was the B2? 1.6. What was the distance? 1.65 meter, right? So we'll get this value 326 kilonewton. Now we can also calculate here also intensity on the B1 side. So Q naught into B1, that is 197.6 into 3.8. You will get this value, right? And length is given. So you can see this distribution, the pressure distribution, and we can see the intensity is varying from left to right, and it's always increasing. It always increasing. So this is called uniformly varying load. UVL, uniformly varying load. To draw the shear force, let's calculate another thing also. Like you can see slope, like I'm drawing the horizontal line. Okay, so this will be the always 326. Okay, so this will be here 4 to 4, right? Okay, so this total length is 6.5 meter. So this total length is 6.5 meter. So now we can calculate the slope. So here we will get the one relation that at every point, suppose this point is x distance from the left side. So we'll get 326.65.36 into x. Means by putting the value of x, we will get the intensity at different location. Suppose x will be put here, then we will get at this point what will be the total intensity at this point, right? Okay, so now we can calculate the shear force diagram. We can draw the shear force diagram. See, what is the shear force diagram? Just at any location, at any point, whatever the shear force, what is the shear force? Either you can consider from the left or right. So you will get the total resultant shear force, resultant loads in the lateral direction. You will see a perpendicular to this plane in direction. So you will get the shear force. So at every location, you can draw the shear force diagram, shear force. So that will be called a shear force diagram. So I'm taking some sign convention. You always have to take the sign convention. I'm taking the sign convention this. Okay, I can draw. Okay, so I'm taking this sign convention. It means either I'm coming from the left side, so downward force will be positive and upward force will be negative. Okay, so see, I'm locating some points like A, that is end point. The point B just beneath this load Q2, so this is B, and some point C. I'm assuming the shear force will be 0 at point C. I'm giving the name, and just this is the point D, just below of the load Q1, and end point is E. Okay, so now we can calculate and see in this relation. We will see. I will discuss one by one. So see at a point A, shear force will be, what is shear force? Shear force will be 0. Okay. Now we can calculate shear force at B, just right side of this load, just right side of this load. So what will be the loading? I'm coming from the left, so you will see there is a like this. So this is 326. and this is a 0.25. So by putting the value of x is equal to 0.25, we will get what is this value. So by putting the value of x is equal to 0.25, we will get this value. We are getting 3. I've calculated, so I'm writing over here, and that we have this value, that is I've calculated, so I'm writing 342.34, right? So this is the load in upward direction is coming. So what we will do, we will take the area of this load, so that will be the shear force. That will be the shear force. So now we can calculate and see downward direction, downward load is positive, but this is the upwards. So this will be the negative. So we can write half into length 0.25 into summation of parallel side, that is 326 plus 342.34. So you can get minus 83.54 kilonewton. So we can go, and this is the, you can say this is parabolic. This is not a linear. When the load is UDL, then it will be linear. So I can check the curvature also. So I'm just drawing here. So it will be like this, minus 83.5 minus 83.54 kilonewton. Now you can see when you are going to calculate the shear force at a B on the just left side of this load, so you will get the sudden change in the shear force, and the direction of the concentrated load is 1500. So you will get the plus 1500 when you are calculating the shear force at right side left side of this load. So you will get minus 83.54 plus 1500. So what will be this value? So this value will be plus 1416.46 kilonewton. That is positive. So we'll get sudden change here. 141646 kilonewton. Right. So this is minus. This is positive. Now we can calculate some other places, some other point. So now we can calculate the shear force at a D. So to calculate the D, first we will calculate the shear force at a C. So suppose there is some location, I'm taking the x-axis here. Okay, and that is distance x from this left side. Okay, so we can write a shear force, general expression for shear force at x-axis. So what will the loading condition? First, let's see, discuss loading condition. So load will be like this. This distance is x. Okay, here we'll get 326. Here, what is this value? So in the expression we can write what this value, 326 plus 65.36 x. This is this value. Okay, this is x, and here we are getting one concentrated load, that is q, and q2 is equal to 1500, and this distance is 0.25. Okay, and we are calculating this is x-axis, so we are calculating shear force at this point, right? This axis, right? So we can write general expression. Okay, so we can write general expression. So for this UDL load is acting in upward direction, so this will be in the negative. So we will take the area. So let's calculate this area, half into length, that is x, into summation of parallel side, that is 326 plus 326 plus 65.36 x. This will be the minus. This will be the minus. Then concentrated load is coming, that will be in the plus, that is 1500 kilonewton. Right. So once we will draw where the shear force is 0. So by taking the shear force 0 on x-axis, so we will get the x value. By putting this 0, we will get the x, and that x we can get 3.425 kilometer, the value of x meter. It means you will see at this at a point, suppose this point C, so we'll get shear force 0 at this point, and this point is 3.425 meter from the left side, right? So here shear force will be 0. Now by putting the value x is equal to, put the x is equal to 6.25. 6.25 means we are calculating shear force at D. So you can check it. D point on the left side is 6.25. Totally the 6.5 by minus, by taking the minus 0.25, so we'll get 6.25. So putting x is equal to 6.25, you can get the shear force at D, and just from the left side of Q1 load, sorry, right side of Q1 load, so that we get minus 1814 0.1825 kilonewton. So we get this value. Okay. See, this shear force diagram is not, it's parabolic, not linear. So suppose I'm getting this this load is D point is here. So I'm getting this value is 1 minus 1814.18. You can write 3 kilonewton like this. And then we meet the point here to here. This should not be linear. It's look like linear, but it can't be linear. Okay. Suppose C point is here. Okay. This is not linear. Okay. See, we get this value. Okay. Now at the point D, there is a concentrated load is acting. So that is in the vertical downward direction. That will be positive. So by adding 2 plus, you will get some value. So that I'm writing. You get the sudden change in the shear force. That will be the 185. Sorry. Okay. That is 185.82 kilonewton. See, I'm writing somewhere 0.82, 0.13. So whenever you are writing in the 0.83, 0.84, so do not confuse with this. You can take the overall. So once you will see the at a point D, their force is 0. So that will be like this. Okay. So this is the shear force diagram we have drawn. Okay, and you can see at this point, at the point D, this point is E. So you will see at a point D, C, and B, there is a maximum or minimum bending moment. So you have to locate then what will be the bending moment at a point D, what will be the bending moment at a point C, what will be the bending moment at a point B. So we have to find bending moment and B, C, and D point, right? Because here the shear force are 0, right? Okay. So now we can go for draw the bending moment diagram. Bending moment diagram. So let me create something. So we can take the sign convention for draw this bending moment diagram. So sign convention I'm taking this. If we are coming from the left side, then clockwise direction will be, clockwise bending moment will be this positive, and anti-clockwise will be negative. So we'll follow this sign convention. Okay, here I'm locating at every point. You can get 326.65.36 x, and this distance is x from the left side. Okay, here also you can divide in this horizontal line. So at every point the extra will come, that is 65.36x, right? Again locate some point A, B here whenever the point C. Now we know where is the point C, that is 3.25 meter from the left, right? And here the point D and point E. So we know bending moment at a point A and this E will be zero. Will be zero. So we have to calculate the bending moment at a point B, C, and D. So let's go to calculate. Okay, so I'm going to calculate bending moment at a point B. So there is a load condition. First, let's discuss. On the left side there is 326. On the right side there is the 342.34. Okay, and here is the distance 0.25. So this is the loading in upper direction. So upper direction load is this will be give us the anti-clockwise bending moment. So that will be negative. Okay, so what we will do, we will just divide this whole load, this trapezoidal section in the two, divided in the two section. One section is a rectangular, other is a triangular. So this will be the 326 and this will be the 65.36 x equal. By putting the x is equal to 0.2, we can get 16.34. Directly we can draw also this, go for the trapezoidal also, but we have to apply this centroid distance. But we know about the rectangular, that is L by 2, and we know about the center of this this triangle, that is H by 3. So that will be easy in the calculation. So I'm going to calculate the bending moment at a point B. So minus, now first I'm going to calculate bending moment for the rectangular. So that will be 326 into 0.25. This is the load. Now lever arm we can write. So we are calculating here. So center will be here. So that will be the 0.25 divided by 2 minus. Now we can go for the triangle. So half into, first calculate the area, 16.34 into this 326. No, this is not 37, 0.25. Okay, so this is the area. Now we can calculate, we can multiply this. This is the center of gravity. Center of gravity which here, that is h by 3. Okay, from the here, right? So we can write 0.25 divided by 3. So we can calculate and we can get this value, that we are getting minus 10.36 kilonewton meter. And that will be also not in the this linear. So that will be parabolic. So that we can write minus 10.3 kilonewton meter. Now, B is clear. Now we can calculate the bending moment at a point C. So what will be the loading pattern from the left at a C? So this point is C, this point is A. Here the load is coming 1500 at a point B. So this is 326. This also we can divide in the two parts. Rectangular part will be 326 and this part will be 65.36x, where x is 3.425. Right. So we can calculate bending moment at a C. So we can write this loading pattern rectangular I'm calculating. So this will be the minus 326 into x. I'm writing x. We can we can put the x is equal to 3.425. So I'm writing now. I'm writing x. X. So this is the what load into distance from here to center of gravity will be x by 2. So x by 2 minus. I'm writing for this triangle. So that's half into 60. Sorry, 65.36x into distance x. And what will be the center of gravity distance from this C? So that will be x by 3, right? Now we can go for the load. 1500 load that is in downward direction. Means it will give us the point at a point C, the clockwise direction, clockwise moment. So that is we have considered positive. So 1500. What is the distance? So distance is x minus 0.25, because x is the distance from the left from here. Okay, so we have to deduct this value 0.25. So by putting the value, put the x is equal to 3.4225 meter, you will get bending moment at C 2412.74 kilonewton meter. And that is in positive, that is positive. So here it will be somewhere here at a point C, just at a point C, that is 2412.74 kilonewton meter. Okay, so that will be maximum because shear force at the point C is 0. Now we can calculate shear force, so bending moment at a point D, right? So let me get something. Okay. So now we can calculate at a point D. So first see the loading diagram at a point D. Or either you can put the value of in this previous relation, you can put this. I'm going to take this relation. No. In the previous equation, you can put the value x is equal to 6.25. So you can get this bending moment at D. Bending moment at D. Right. You can see the loading diagram also. So that I'm writing here. Here will be 326. Here Q, that is 1500. Here is this you can divide in two parts. So this is 326 and this would be the 65.36x, and this x would be 6.25 from the left. So I put in the value 6x equal to 6.25, we can get the bending moment at D. So that we can get, I have already calculated, so I'm writing, so that we can get minus 96.69 kilonewton meter. So that we can write here, that is negative at this point B, at a point this D. So this is E, this is D. Okay, this is point C, this is A, this is B. So here that is we get 96.69 kilonewton meter. So now we can calculate. So here it will be here. So that will be in the curvature, you can check. So you can see there is a minimum, here is the local minimum, we can say, for this curve at a point B. Here the maximum bending moment at a point C. Here is the bending moment. So you can see at this point B, C, D, there is either maximum or minimum bending moment, because the shear force were the 0 at point B, C, and D. So this is the bending moment diagram. Okay, so once we have drawn the bending moment diagram, shear force diagram, so our work is over at a geotechnical point of view. Okay, so by drawing the shear force diagram and bending moment diagram, we can calculate and we can get the value of every section That's shear force and bending moment diagram value. So these are some reference that I've taken to make this PPT, this lecture. So thank you. In the next lecture, I'm going to discuss design of a strap footing. So that is very important. And there is also some procedure and some steps that I will discuss and in the next lecture. So thank you.